does not fit into path cost or goal state. You don't consider here the path cost of the path or goal state formulation. Local search can do quite well on these problems. I'll tell you the figure. Local search algorithms operate by searching from the start state to neighboring state without keeping track of the paths nor the set of states that have been. They don't store any of the states. It will store only the current state, and whichever it will be selecting the neighboring state, only that will be stored. So there is very little memory. They can often find reasonable solutions. And optimization problems are also possible to solve by local search algorithms. And how do you do this searching? Means by taking the objective function. And here you will be having the terms like global maximum, local maximum, flat global maximum, global minimum. These are the terms we use in this local search and optimization. So if you see, this is a simple state space and versus objective function. If you take, and this is the graph where you have certain terms. So this is a state space if you consider and calculate the objective function. So this is my graph. So I want to travel this graph. So while traveling this graph, you have the points like this is called the global maximum, and this is the local maximum, and this is the flat local maximum, and this is the shoulder. So for example, now if you are traveling like this, okay, so you want to reach this global maximum, that is your target actually. So this is like this. If we go through this graph, this is now I am here. So in the current state, I am here. So I can go here in order to reach the local maximum. And you have one more thing called flat local maximum here. So understand, like remember these terms. We'll be using this later. Madam class. Hill climbing algorithms is a heuristic search algorithm. It's a heuristic search algorithm which continuously moves in the direction of increasing value. So this hill climbing algorithm continuously it will move in the direction of increasing value. So whenever you start from here, okay, so your value, if it is increasing, your neighbor value is increasing, then only it will take that move. Otherwise, it won't take that move in the hill climbing algorithm. That is why it is hill climbing. Means you will be moving in the path in order to reach your goal. If the current state, if there is a better state than the current state, then it will take that move. Okay. To find the peak of the mountain or the best solution to the problem. It keeps track of one current state and on each iteration moves to the neighboring state with highest value. That is, it heads in the direction that provides the steepest ascent. If only if you have any steepest ascent, increasing value, then only this algorithm will take the next state. So some problems you will occur different regions. Local maximum is one region. This is local maximum. The state which is better than its neighboring states, but there is also another state which is higher than it. So if you consider here, this is a local maximum, but this is not the goal state. Goal state is which is the global maximum. Okay, so if at all somewhere you get this steep as local maximum and a steep wave is higher than all as global maximum. So global maximum is the best possible state of state space landscape. It has the highest value of objective function. So your goal is to always to reach the global maximum, not the local maximum. Okay, current state means it is a state in a landscape diagram where an agent is currently present. So I am here now. So where I am present, my current state is that. Flat local maximum is a flat space in the landscape. So if now, for all you are moving like this, so for some distance, it is flat. Means all your neighboring states have the same value. So that we will be calling as the flat local maximum. So climbing search algorithm, which is the most basic local search technique, at each step the current node is replaced by the best neighbor. So if you are moving or you are climbing some hill, so what happens always when you are climbing the hill, your next step will be always higher than your previous state, right? So you'll be moving high to the highest level. So you want to climb a hill, always your next step will be will be higher. It will steeper than the previous step. That's why it is called a hill climbing search algorithm. So return state is local maximum. So you'll be at initial state and you select your neighbor, which is the highest value. So if it is having the neighbor is having the highest value, then that neighbor will become your next current state. So the neighbor will become the next current state. Like that, till you reach your maximum local, that is local maximum, global maximum, you will continue this process. So there are certain problems in hill climbing algorithm also. If you take this local maximum, so there are certain problems. One is local maximum, plateau is one problem. Okay. So we'll discuss few problems here. What are the problems you can get in this hill climbing means? One is local maximum. See, whenever you are traveling like this, so next state is higher, steeper than this. So you go, you reach this state. And you reach this state. After that, you reach maximum. After that, when you compare with this with next state, it is smaller, right? Well, this is like it is declining here. Fall. There is a fall here. So this value will be less than this local maxima. So it will think that this is the goal state and it will stop the search. So a local maxima is a peak state in the landscape which is better than each of its neighboring states. But there is another state also present. So what is the solution for this means? Backtracking technique can be a solution of the local maxima, but in hill climbing, backtracking is not allowed. So this is the problem you get occur in this while you consider this hill climbing algorithm. Next is plateau. Plateau is a problem. Plateau means a flat area like this of the search space in which all the neighboring states of the current state contain the same value. See, all the neighboring states same value. So what the search algorithm will think? So because it is having the same value, so we have reached our maximum value and it will stop the search here because of this algorithm does not find any best direction to move. So hill climbing search might be lost in the plateau area. If in your algorithm searches, if this is the plateau, if you get this flat maximum, then you can't reach this higher global maxima. It will think that this is the maximum value and it will stop the search there. So this is one problem here. So what is the solution means? The solution for the plateau is to take big steps while searching to solve the problem. Instead of taking small steps and you think that this is the maximum point where we have reached. So take the big steps so that you can maybe you will get here and you'll get to know that okay here there is a steep So then you can move this. Otherwise, what you will think? So you think that this is a flat value, equal values are there. So this is the main steepest ascent, and your algorithm may stop here. So that is one problem in hill climbing. Okay, so one more in this hill climbing, we can even consider the end queens, right? So we can using this hill climbing, even n queens problem can be solved. Means with no two queens in the same row. So you just move and you will be, you can use this hill climbing in this n queens problem. So what is the heuristic you can take as number of pairs of wings that are attacking each other. So if you take here we'll be getting like h is equal to heuristic value 17 for the above state. So in order to do this n queens, state means all 8 queens on the board in some configuration, and successor function. What is the successor function for this n queens means move a single queen to another square in the same column. So you can move like this, right? The above. So such that no queen should be in the same column. So like that you can move that. That can be your successor function. An example in the number of pairs of queens that are attacking each other. So what is the heuristic function here means? We have to always in this such problems we'll be minimizing the heuristic functions. So heuristic function here means what are the pairs of queens that are attacking each other? Means how many, if I move here, this queen to here, already this queen is there here, this queen is there. So what that H value will become the number of pairs of queens that are attacking each other. So if you see here, by using this hill climbing, we have solved this n queens problem such that no two queens should be in the same row and same column. So if you so randomly you can generate 8 queens starting states. So how to do that means 14% of the time it solves the problem. 86% of the time if you use hill climbing for this 8 queens, it gets stuck at local minimum. So we have seen, right, what is local minimum means. At the below side if you have this, where local maxima is there. Local minima means here. At the this local maxima, and at the end here this is local minima. This so next, escaping shoulders. So we have seen what is meant by shoulder right here. This is called shoulder. Shoulder is something like a flat, but a small shoulder. So whenever you are moving here, 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 so there you got a flat. Okay, so when values are same, and then if you move that like a plateau only, and if you can move that, then you will get this reach to a global maximum. So how to escape this shoulders means sideways move. So if no downhill, uphill moves, allow only sideways moves in hopes that algorithm can escape. Means we have to need to place a limit on the possible number of sideways moves to avoid infinite loops. So we can keep a limit here in order to stop there, because if the shoulder comes, it is also a flat, right? So sometimes algorithm can stop there. So in order to avoid that, we can keep some limit of 100 moves. So if at all, if within that 100 moves, if there is any increase in the value, then you can continue. So if you do like that, when you do some limit here of 100 moves, 100 states, so like percentage of problems solved from 14 to 94% problems are solved. So keeping a limit on the moves, because if you get a shoulder, don't stop there. Keep a certain limit, and in that limit, you can move, right? So if you keep a limit, then raise a percentage of the problem from 14 to 94%. Close the door. So next is in the hill climbing, we'll see the stochastic variations. The stochastic is something like taking the random probability distribution, or a pattern may not be predicted, but you take some random value that we call it as a stochastic. The stochastic hill climbing. So you select the random selection among the uphill moves. The selection probability can vary with the steepness of the uphill move. So in order to avoid this local minima getting stuck there, we have three types. One is random walk hill climbing, random restart hill climbing with both. So when the state space landscape has local minima, any search that moves only in the greedy direction cannot be complete. Random walk, on the other hand, is asymptotic complete. So put random walk into greedy hill climbing. So with the random restart, so hill climbing with random restart means if at first, if you don't succeed, try again, go to next part, then go to next part, like that, don't stop there. That is random restart. So here we will be, for each restart, run until termination versus run for a fixed time. So for a fixed number of restarts or run indefinitely. So you have to restart again, don't stop there, and fixed number of restarts, you have to run and go ahead. So say each search has the probability P of success. For 8 queens, P is equal to 0.14 with no sideways moves. So what are the expected number of restarts, expected number of steps taken? So we have to think like that, and we have to next go to the next step. So if you stop there, then your hill climbing will stop. So in order to avoid that, we are using this random moves. Go to some randomly go to move to some other state, and from there you have to search that and restart that. So that you have to do this stochastic. So in order to overcome the problems which are there in the hill climbing, like plateau. Okay, so plateau is one problem you have seen, right? Plateau is one problem, local maximum is one problem. So in order to overcome that, we will be using this stochastic variations. In the stochastic variations, we will be using this random walk hill climbing, random restart hill climbing with both. Restart means, so randomly you select one point, from there again you have to restart your search. Locally, not globally. This hill climbing is a blindfolded search. See, if you are climbing the hill, if you are not blindfolded, you know how to go. Okay, so where there is a plateau, but a person with a blindfolded. Okay, so he like he what can we say? Some cloth is tied to his eyes, and now he is blindfolded. He can't see. Then that blindfolded person, if he wants to climb a hill, that is the correct example of this hill climbing, because it is blindfolded. We don't know the entire exact what is the environment. We know only a certain local area. So we will go there to that local area and we will see whether that is the our goal or not. So in order to reach our goal, some problems may come in this hill climbing. One is a flat land is there. If you get this flat land, then you think that okay, other next state also will have the same, right, in the flat land. So you think that this is the goal state and your search algorithm will stop there. That is one problem. And local maxima is you go to certain height there and you think that that is the highest point. So that is the goal. But when you go when you go to the next step, there again you have to come down of that. Again there will be somewhere the global maxima. So you will get these problems because you don't know the entire picture of the state space. So you don't know where your goal state is there, and sometimes there is a problem with this hill climbing. Next, hill climbing with random walk. So what you have to do in this random walk means at each step you have to do one of the two. One is greedy. Probability, some probability, move to the neighbor with largest value. So which largest, you select the largest value and you with some probability and move to that neighbor, or with randomly with probability 1 minus p, move to a random neighbor. So you can do any one with the random walk. Okay, this is one thing. Next, hill climbing with both. So at each step, do one of the three. You can move with greedy method. Greedy means move to the neighbor with the largest value, or you can do the random walk or move to a random neighbor, or random restart, resample a new current state. So you have to change your current state to some random value. From there, you have to restart. So these are the three steps you have to do in the hill climbing. Seen already. So this is about your hill climbing. Mostly with this hill climbing, what is the advantage? Memory will be less memory is used compared to your A star or that. And this is greedy search and it's a local search. You don't know the exact, the entire global path or where is your goal. You don't know the entire state space is not known here. Only whenever you go, you know the next state. So select the next state. If the next state is better than the current state, then you make the next state as the current state. So that is the main basic algorithm we use here. So what are the problems you get here means one is local maxima is the problem. Next is plateau is the problem. So in order to overcome these problems, we have certain variations in this hill climbing. They are stochastic variations. So what are the methods we use here in stochastic means three types. Random walk hill climbing, random restart hill climbing with both. Next is simulated annealing. So simulated annealing is also one of the local search techniques. But here It allows downward steps. Hill climbing, always you will be moving in the forward direction, whereas in simulated annealing, even the downward steps is also allowed. And this simulated annealing is taken from the physics. You have the annealing in physics where it is a process where we'll be using our metallurgy. The metals are slowly cooled to make them to reach the state of low energy, where they are very strong. By using this annealing process, we make that metal to cool and to make them to reach a state of low energy from high energy. This is the process of annealing process. So in metallurgy, we use this annealing. So we have taken here this annealing concept in order to make the twist on random walk. So what is the basic idea we use here in simulated annealing is like hill climbing. In this annealing also, you identify the quality of the local improvements. So which is better? So next, which state is better than the current state? So instead of picking the best move, what we do here is in hill climbing, always we will compare them with a neighbor, and if the neighbor state is better than the current state, then we make our neighbor as the current state. But here, what we'll do is we'll pick one state randomly. Okay, any state, that can be any state. Say the change in objective function is some delta. If delta is positive, then move to that state. Okay. Otherwise, move to the state with probability proportional to delta. Thus, its worst moves, very large negative delta are executed less often. However, there is always a chance of escaping from local maxima. Here you can come backwards, and from there you can move forward, and you can check whether there is any, if at all local maxima is there. If you move, then at least again you have the path of steepest ascent, and from there you can come to the global maximum. Like if you want to some interpretation of the simulated annealing, imagine letting a ball roll downhill on the function surface. So there is a rolling surface. So if you keep the ball on at the top, like for minimization, so it will roll downhill, right, on the function surface. Now imagine shaking the surface when the ball rolls, gradually reducing the amount of shaking. Like whenever you reduce the amount of shaking, so slowly it will come down, not with the same speed, but it reduces the speed, right? So this is like simulated annealing. So whenever you want to take the path, okay, so by using this simulated annealing, you come to down, even you can come this downwards, and if you go and check where any other states are there, and from there you can jump to the current state if there is any other uh, steepest ascent is there. It's a physical process of cooling a liquid or metal until particles achieve a certain frozen crystal state. So what the annealing will do, it will convert this liquid into frozen crystal states. Just answer your roll calls.